Hello, everyone. Welcome to part 2 of Dart Injections, where we try to learn Dart as quickly as we can. So, without any further ado, let's get to it. All right. As a quick recap, last time we finished the overall introduction to Dart. We went through variables, operators, comments, and then we went through some types, right? Through built-in types, basically through all the basics. So numbers, strings, booleans, records. Wait, it supports all of this, but we learned only about numbers, strings, booleans, overall like a little hint about runes and grapheme clusters, and symbols, which I don't think we'll be using anytime soon. But it's good to know that there is, the concept of symbols. So let's start going into some more interesting parts of, structuring our data, because that's where half the problems are, depending on how you're going to structure your data. Different kind of problems you're going to either solve or create. Alrighty, so records. And version node, records require language version of at least 3.0. So it's good to see that language is still being developed, because I recall that Dart, it's been out there for quite a time, at least as long as Flutter is, which is many years by now. So it's good to see that it's still being evolved. Records are an anonymous, immutable aggregate type. Okay, anonymous as in they don't have a specific... Wait, you don't name them. Okay. Immutable as in we can't change the value assigned to it. And aggregate type, I guess, as in they aggregate multiple other base types. So like other collection types, they let you bundle multiple objects into a single object. Unlike other collection types, records are fixed sized, heterogeneous, and typed. This word is just tripping me up every time. Heterogeneous? I don't know. I have no idea. When I hear it, it's like, oh, duh. But I can't come up with a pronunciation myself. So they are fixed size, heterogeneous, and typed. Okay. Records are real values. Okay, you can store them in variables, nest them, pass them to and from functions, and store them in data structures such as lists, maps, and sets. Yep, so it's just like any other value. Great. As in, there are no weird cases with them. That's how I understand that. Okay, so let's look at how we can, define some records. So records expressions are comma-delimited lists of named or positional fields, enclosed in parentheses. Okay, this is like really dense. So record expressions, I guess things that produce a record, are comma-delimited. Therefore, we have our, we say, oh, our variable record will hold, and this will produce, this is our record expression, right? And it's a comma-delimited list. So we have something, comma, something, comma, something, something, right? Of named or positional fields. Not and, it's or. So that's interesting. Okay, so we have named or positional fields. So the first one is not named. If this field isn't named, it's just a value, right? So some value that holds a string. But this one is positional. It's named. Has A. This one is B with some value, right? And this one is again positional. So the way I can see it is that we define, what the hell, why is it at the end? That means that this one needs to be first, this one needs to be fourth, but these two can be swapped? Maybe. Record type annotations are comma-delimited lists of types enclosed in parentheses. You can use record type annotations to define return types and parameter types. For example, the following int statements are record type annotations. So this is what normally would be called a tuple, right? In many other languages. Here is just referred to as record. So we have a function swap that returns this record of 2 integers. And it takes also an input of 2 integers, and we just swap them. So looks like we have some kind of destructuring here, where we take our record and we extract first integer and second integer into A and B, and then we build a return record just swapped. Okay, so it's good to see that we can restructure that. Let me just check comments just in case somebody sneakily commented, but no sneak comments. All right. So fields in record expressions and type annotations mirror how parameters and arguments work in functions. Okay, so I guess in functions we can also have a combination of named or positional fields. Positional fields go directly inside the parentheses. So record type annotations and a variable declaration. So we have string and int, right? Initialize it with a record expression. Hello, Taras. How are you doing? It's good. It's nice you're joining. And for the record, we're talking about records. So we need to initialize it. The first one is string, so we gave it a string. The second one is supposed to be integer, so we gave it an integer. Great. In the record type annotation, named fields go inside a curly brace delimited section of type and name pairs after all positional fields. Okay. In a record expression, the names go before each field with a colon after. Okay, so record type annotation and a variable declaration. So we define a variable which is a record with those 2 named fields. Oh, so this is a declaration of it, right? While this here was a definition, whatever. We define what it's... Wait, here we actually create an instance of a record, right? And we use those labels without any fancy curly brackets. While here, when we define the record type, we need to kind of separate them. Interesting. That's unexpected. And the record expression, the names go before each field value and a colon after. Yeah. So exactly. So when we define it, we say integer A, boolean B, just like if we were defining a variable, right? We define variable by specifying a type and then the name. While we're initializing, we have record equals, and now we can just say that A is 1, 2, 3, B is true, and we could probably easily just swap them, and that'll be fine. Let's reopen our try dart so that we have it here, and we can just copy and paste, right, to experiment. I actually want to take this one. So in record condition, named fields go inside a curly brace delimited section of type and name pairs after all positional fields. Okay, so if we have the annotation, so let's paste it here, or wait. Let's make it like this. Instead of var, we're gonna say that we have a type record, and this will be our record, right? We won't assign a value to it. So our record will be basically, so our first field should be string. Second position field should be last. Sorry, string as well. And then we have in curly brackets, int A and bool B. Okay? That's how I understand we should be able to define it. And now we should be able to assign it. So our record is this. So now all those named fields, I guess we can just throw in wherever we want, because as long as they are named, the compiler knows that, oh, I just need to put them at the end. It's all gonna be fine, right? And I can just swap B with A, and it doesn't matter. Okay, I could even throw them in the beginning, and it should be still fine because there's our name. They will be ignored. This is the first name, the first positional and second positional one. Okay, great. And there says int A is 1, B is 2, AB is BA. Yep, that's the swap. Yeah, yeah. Okay. Oh yeah, Taz, you're just sharing like a quick way to do a swap, right? As in we define integer A and integer B, right? And then by using destructuring, we can destructure this directly into existing variables. Okay, and now these numbers are grayed out. No, they're just grayed out just for fun. Okay, great. And we can do print. Wait, how is the printing going? I forgot how to print. Let me just undo. Oh, just print. Okay, so it was just print. So we can say print our record, and we just throw in our record. Let's see if this works. Yep, our record worked. There we go. And look how it actually did the positional first, then is the second positional, and then it put in the named fields in order they were defined here in our type definition. Okay, I see. So that's very, very clear now. Good. So next, the names of named fields in a record type are part of the record's type definition, or its shape. Two records with named field with different names have different types. Okay. All right. So basically, if we have a definition with field A and field B, it's incompatible with field X and Y. At least when it comes to the named parts. Okay. In the record type annotation, you can also name the positional fields, but these names are purely for documentation and don't affect the record's type. Oh, so I can do that, and these two will be compatible, right? Okay. Because they're not in parentheses. Okay. I mean, whatever, curly brackets. I see. Okay. So I can still name them. Here the names are ignored. Kind of confusing if you're not looking for it specifically, but at the same time, nice. Okay. I can see that this is something very useful, especially as, little like for as little interfaces or some part of function in and out, you can name those without restricting this specific thing, and therefore you can maintain compatibility. That's great. Okay, this is similar to how positional parameters in function declarations or function type def can have names, but those names don't affect the signature of the function. For more information and examples, check out record types and record equality. I like how they're tying it to, hey, this works exactly the same as in functions. That's actually really nice. You have some kind of thing to consider the same, some kind of link between those. So that's nice. Okay, now we're moving to record fields. Record fields are accessible through built-in getters. Records are immutable, so fields do not have setters. Okay, makes sense. Named fields expose getters of the same name. Positional fields expose getters of the same dollar position. Skipping name fields. Oh, okay. Record and number 1. Whatever. We'll print out first. Interesting. To streamline record fields access even more, check out the page on patterns. Okay, so this is basically in a way that, okay, it automatically defines the field, as in we can use dot and the name of the field, right? Or the number of the field. And that's pretty much it. At first, I thought we'll be defining our own fields or something. Like our own getters on a record type. Okay, record types. There are no type declaration for individual record types. Records are structurally typed based on the types of their fields. Okay, so this is like, hey, we are using duck typing here. As in, if it has the same shape, they are equal, right? And for position parameters is just the type. For name parameters is type and the name. But it doesn't matter really. We don't name those. Like, you can't have two separate records as two different types. They have the same shape. They are the same thing. A record's shape, the set of its fields, the field's types, and their names, if any, uniquely determines the type of record. There we go. Hello, Pancake Dev. Long time no see. I guess because long time no stream for me, right? How are you doing these days? Each field in a record has its own type. Field types can differ within the same record. The type system is aware of each field's type whenever it is accessed from the record. Okay. Field types within the same record. I guess, yeah, because a record can have set of different types that it holds. Yep. Like a number and a string. And it knows that first one and second one are those, so it's all good. Wait a moment. Number 2, static type object. Runtime type string. Wait a moment. The type system is aware of each field's type wherever it is accessed from the record. Okay, so number is like the parent of integer, right? While object is the parent of string, at least as far as we know right now. So, I'm not sure what they're trying to say here. Because they're two unrelated libraries that create records with the same set of fields. The type system understands that those records are the same type, even though the libraries are not coupled to each other. Exactly, that's what I was trying to say, that for compatibility, like little interfaces or whatnot, it's great because if you have a library that creates a 2 or 3D point in space with, like, floating point numbers, like here we have doubles, and suddenly you want to use some extra library for math for those things, for like vector math or something, suddenly you can use the same type and things are compatible. At least for those, obvious things. Without having some kind of common other library that defines those types. Okay, record equality. Two records are equal if they have the same shape, set of fields, and their corresponding fields have the same values. Okay. Since named field order is not part of record's shape, the order of named fields does not affect equality. But this is only for named fields. Other positional ones, they matter. These are all positional. So if 1, 2, 3 is there, here their names don't matter because they're just positional. So these two will be equal. Exactly. Well, here we have the name parameters, right? So because we have those parentheses, and therefore those two, even though they also have the same types, but they have different names, so they won't be equal. There we go. Points false. Equals on unrelated types. Yep, it won't even let you compare them because from the perspective of the compiler, these are completely two different types. While here they are the same. Okay, records automatically define hash code and equals method based on the structure of their fields. Yep, that's great. So this is kind of similar what I guess record classes want to do in .NET. It's just in .NET it's full-fledged class, but it also defines a bunch of those, equals and hash and several other things for you. Okay, but it's nice and lightweight, understandable. Okay, so let's go to multiple returns. Records allow functions to return multiple values bundled together. To retrieve record values from a return, destructure the values into local variables using pattern matching. Why does the structure? Oh, the structure leads to language patterns. Okay, so the structuring is considered a pattern. All right. Okay, so returns multiple values in a record. So we say that this user info returns this record of a string and an integer. We'll name it, for convenience, name and age. And it takes in basically a map of some JSON, basically JSON. Could be anything, right? So this is the first time we actually see the dynamic being used. Interesting. And what we're returning is JSON. Okay, we take the name field and we let's call it cast it to a string, right? And here this is gonna get cast to int, and that's what we're returning. So we created this record here because we have open parentheses, some kind of value, comma, value, and we close the parentheses. Okay, that's very simple. And here we define our function, right? So we define our JSON, and there we go. I guess that's how we can define it. Great. That's a nice example. I like that. I guess we'll learn about maps in the future. And then the structures using a record pattern of positional fields. Because these are positional, so we can just say, hey, we call to whatever, get the user info, right? And we plop it into variables name and age because we destructured it. So this is equivalent to var info and name is this, age is that. There we go. Beautiful. And whatever names we're going to give it here, they don't matter. Absolutely don't matter because these are new variables we're creating depending on the positional parameter. But I wonder how extracting named parameters would work because I can see often being like, hey, I want to destructure this record, but I don't want the thing named ABC to be specifically variable ABC. I want to give it a different name. So something tells me there would be some kind of something as something syntax, maybe in the next paragraph or something. You can also destructure a record using its named fields. There we go, using the colon syntax, which you can read more about on the pattern, on the pattern types page. So we have this time user info returns actual named fields in a record. So under structuring, we can say name and colon age. Okay, I guess we'll learn about how to rename them if there's such feature later. You can return multiple values from a function without records, but other methods come with downsides. For example, creating a class is much more verbose, and using other collection types like list or map loses type safety. Or just creates overhead, right? Because a list or a map might actually create overhead because there's a bunch of stuff that's being created around it behind the scenes. Possibly. Okay. Note. Records multiple return and heterogeneous type characteristics enable parallelization of features of different types, which you can read about in the Dart async documentation. Okay, we're gonna look into that, definitely. Okay. Records as simple data structures. Records only hold data. When that's all you need, they're immediately available and easy to use without needing to declare any new classes. For a simple list of data tuples that all have the same shape, a list of records is the most direct representation. Take this list of button definitions, for example. So final buttons, it's a list, and we have one record and two records in it. Two records. So first record is, these are positional, okay? So label button I or button 1, icon, right? And on pressed, we actually throw in a function in here. Why not? And then another one, which also has the same positional parameters. This code can be written directly without needing any additional declarations. Exactly. Records and typedefs. You can choose to use typedefs to give the record type itself a name and use that rather than writing out the full record type. This method allows you to state that some fields can be null, even if none of the current entries in the list have a null value. Okay? So you have type definition, button item, and we just define that, hey, this is a specific, record, and here we're using named fields. In this case, we also define it as function. Okay, so the type of the function, when we define it, looks like you have return type, the keyword function, and what it takes. Okay, and we also make it nullable. Okay. And then we can, because we define this as a little separate type definition, something like an alias for it. Alias for this definition, we can just reuse it here. And instead of copy pasting, we just have one thing to refer to. But essentially, it's like, okay, compiler sees this. Oh, I know that I need to replace this with that and just paste it in there, and that's it. So it's, something they call sugar, right? Syntax sugar, but very nice sugar. All right, because record types are structural types, giving a name like button item only introduces an alias that makes it easier to refer to structural type BAM. Having all your code refer to a record type by its alias makes it easier to later change the record's implementation without needing to update every reference. Exactly. Code can work with the given button definitions the same way it would with simple class instances. Yeah, so list container, widget, and list of for each button, and we just iterate over them, right? Button, and we create a call a function container and give it stuff. And child, we just get the stuff out of the button. There we go. Beautiful. You could even decide to later change the record type to a class type to add methods. Yeah, because you can just replace that class button item, right? And because this was already reused everywhere, it just works. Yep. So let's look at the class button item. We have its definition. We have final string label, so therefore it will be read-only, just like in records. Icon and the function, all great. And we just added a constructor. So we just require the fields, right? Okay. So I don't remember what were those curly brackets here for. Because it looks like it tries to be like a record with named fields. And then we have has on pressed, I'll just extra getter to get some extra functionality out of that. And that's that. So it looks like we can define extra things on top of a record. I wonder if with extension methods or something like that, we will be able to actually add things to something like a record, because that will be very useful. Or to an extension type. Oh, so we can actually define extension type button item. And this has some wacky functionality with lots of parentheses. What the hell? Okay. And string get label. Okay, we define those things. So we haven't learned about extension types yet. So sure, why not? Extension type. That's not extension methods, extension type. So yeah, we haven't learned about that either. And then create the list of button definitions using the types constructors. Yep, there we go. Again, all while not needing to change the code. Excuse me. That uses that list. Great. Changing any type does require the code using it to be very careful about not making assumptions. A type alias that does not offer any protection or guarantee for the code using it as a reference, that the value being aliased is a record. Extension types also offer little protection. Only a class can provide full abstraction and encapsulation. There we go. Okay. So basically the verdict is records are cool. Very useful. So now let's go into collections. Let's see how Dart solves collections. Because so far we learned about lists, and at the first sight they were okay, nothing crazy, just standard stuff. Alrighty. Dart has built-in support for list, set, and map collections. To learn more about configuring the types collections contain, check out generics. Okay, to configure the types collections contain. Oh, as in you provide generic types. Great. Okay. Lists. Perhaps the most common collection in nearly every programming language is the array, or ordered group of objects. In Dart, arrays are list objects. So most people just call them lists. Okay, so I guess we don't have a separation between an array and a list. Okay, I can live with that. Dart list literals are denoted by a comma-separated list of elements enclosed in square brackets. Each element is usually an expression. Here's a simple Dart list. Okay, there we go. Dart infers that list has a type of list integer. Okay, so it actually infers that. It doesn't say that, oh, this is list of objects, right? If you try to add non-integer object to this list, the analyzer or runtime raises an error. For more information, read about type inference. You can add a comma after the last item in Dart collection literal. Okay, this trailing comma doesn't affect the collection, but it can prevent copy-paste errors. Yep. And they don't have a comma here. So let's just see. We have our lovely list that we are our list. We're gonna just plop it here, right? Run. There you go. Here's our list. But we can throw in a comma and it should be happy, right? Great. Here it doesn't mean much, but if you have a more complex list, you know, you can basically ensure that each element ends with a comma. Therefore, when you're rearranging things or copy pasting or whatnot, you know, no big deal. Like, oh, this doesn't support any shortcuts. Too bad. I can just cut this and plop it here, and it'll be always fine. And another thing is, in version control, like Git, for example, if suddenly I need to add another thing, right? I don't know, spaceship, right? and put a comma at the end, suddenly in Git, the only thing that happened is a new line was added. If I didn't have that comma here before and needed to add it, suddenly 2 lines are changed and it's harder to read changes, right? It's literally a very tiny thing, but somehow it makes me happy. Alrighty, let's use zero-based indexing, where 0 is the index of the first element and the list length -1 is the index of the last element. All standard. Great. You can get a list's length using the .length property. Great. Property, property. And access a list's elements using the subscript operator. Okay, there we go. This length is, we're checking if it's actually 3 elements. It should be. We check that the element number 2 is, well, no, the second element, because 0 is the first and 1 is the second, is 2. There we go. And we can also assign that, hey, now the second element of the list will be 1. So it'll be 1, 1, 3, right? There we go. So we can modify them because this one has var as it's a variable. To create a list that's a compile time constant, add const before the list literal. There we go. So now it's compile time. Therefore, we can't change it. So if you try to change the second element, this line will cause an error because no, this is a constant. This won't change. The contents of the list cannot change. Okay, straightforward. For more information about lists, refer to the list section in the Dart core documentation. Okay, so this will be just an overview still. Just an overview, not a proper deep dive into all those subtypes and stuff. Okay, but it's good that we have, like, let's look Dart core here, and we have about lists, right? And we have more about it. And then more about sets and stuff. Okay, this is like a proper documentation. Alrighty. So let's move on to sets. A set in Dart is an unordered collection of unique elements. Dart support for sets is provided by set literals and the set type. Here is a simple Dart set created using set literal. Okay, so this is a set suddenly. So instead of using square brackets, we use curly brackets, and that makes it a set. Okay. So Dart infers that halogens, right, has the type set string. Okay, set of strings. If you try to add wrong type, the analyzer runtime raises an error. There we go. So that's great. To create an empty set, use just curly brackets preceded by the type argument, or assign the curly brackets to a variable of set. Right? So we say variable names is of type string set, right? Or we say, instead of var, we just say, hey, the names has a type set of strings, and we can just assign empty set, and that's it. Okay, and this will create a map, not a set. Interesting. So there's a gotcha. Set or map. The syntax for map literals is similar to that of set literals, because map literals came first. Okay, the just empty curly brackets defaults to the map type. If you forget the type annotation on curly brackets or the variable is assigned to, then Dart creates an object of type map dynamic. Ooh. Wow, okay. A map that can point from anything to anything. Good to know. So add items to an existing set using the add or add all methods. Okay. Okay, so we have our elements, right? Empty set strings. So we can add a single element, or we can add all, and we provide it with a collection, and we'll add everything from the collection. Okay. Okay, I want to try that out. So what we're gonna do, we're gonna print our elements. Okay. And here is unhappy because halogens isn't defined. So we copy this. So we've got our halogens defined up here. Let me just move it because buttons are in the way. Okay, so we have a set of those halogens and we can add that set to this set, right? And it will end up working. But what if I'll make it a list of strings? I believe it should be still working, right? Run it, and it still works. Okay, so this isn't like very picky about type. Any kind of collection will make it happy. All right, so I guess it uses some kind of for each loop in there. And that's it. Okay, so to create, we did the empty, yes, and yes. Use dot length to get the number of items in the set. Okay. To create a set that's a compile time constant, add const before set literal. Okay, so we can have actual compile time set as a constant. That's awesome. Very nice to see that. For more information about sets, just look in the documentation. Great. So now let's move on to maps, because we have maps and then we have tons more in collection. Wow. So yeah, maps. In a map, each element is a key value pair. Each key within a pair is associated with a value, and both keys and values can be any type of object. Okay. Each key can occur only once, although the same value can be associated with multiple different keys. Dart support for maps is provided by map literals and the map type. Here are a couple of simple Dart maps created using map literals. Okay, so again, we start at, our variable gifts. We start with a curly bracket, but here instead of just doing partridge, turtle doves, and golden rings, we actually make it just like in JSON or whatever. We give it a label. In this case, all the keys are strings and values are strings as well. So I guess this will be type of, map of string comma string. And here we have where the keys are numbers while values are strings. Okay, great. Dart infers that gifts has the type of map string string. There you go. And noble gases is the map of int string. If you try to add the wrong type, there will be an error. Okay. You can create the same objects using the map constructor. Okay. So we just say gift. Gifts is we construct a new empty map. And then we just add for the key first, it will be partridge. For the key second, for the key third. And the thing goes here, we just have the numbers as keys. If you come from a language like C# or Java, you might expect to see new map instead of just map. In Dart, the new keyword is optional. Okay. For details, see using constructors. Okay. So we just skip the new. Makes sense because this wouldn't make any other sense. The type isn't a function. So yeah, that's relatively simple. And in C# in theory, if you don't put a new, you can just use a constructor that allows you to skip all this stuff and write it more in this style anyway. Okay, and actually this type will be inferred as well in some cases. All right. To add a new key value pair to an existing map using the subscript assignment operator. Yeah, it looks like this as an operator that you could probably override. But in this case, we just say, hey, fourth as a key is this. That's how we added it. To retrieve the value, we just use the subscript, right? Get me the key, and it will return the value. So partridge is the same as partridge, right? If you look for a key that isn't in a map, you might get you get null in return. So if I'll try to get fifth, it isn't there, it's gonna return a null. So you're not gonna get an error, you're just gonna get null return. That's good to know. And use length to get the number of key value pairs in a map. So wait, I'm gonna get a null in return. That means that, oh, so the return type of this thing should be nullable, whatever is being held. Okay, that complicates some things, but sure, I can live with that. So use length to get a number of key value pairs in the map. Yep, length is 2. To create a map that's a compile time constant, add calls before the map literal. So again, great that we can make constant, constants as little lookup tables. So that's great. But we probably can't do a bunch of calculations to generate them. So that's too bad. I wonder if somebody made like a code generators for Dart. Because I know that, in C#, for example, you have like support where you write type of code that will actually like generate other files of your code in the background. Your IDE will be aware of that, and it's like fully supported thing where it just generates the files in the background during compilation, but then they are used in the actual compilation. So I don't think Dart has that. Again, I'm comparing a lot to C# because I like C#. And this is kind of similar to some extent. Okay, collection elements. So wow, we're just barely through a third of this collection section. Wow. A collection literal contains a series of elements. During runtime, each element is evaluated, producing 0 or more values that are then inserted into the resulting collection. These elements fall into two main categories: leaf elements and control flow elements. So leaf elements, which is inserts an individual item into a collection literal. Okay, so we're talking about collection literals. So basically how we're defining our actual collection instance. Okay, so the leaf element. So it's an expression element, evaluates a single expression and inserts the resulting value into the collection. Okay. Or map entry element, evaluates a pair of key and value expressions. Excuse me. And inserts the resulting entry into the collection. Okay. And then we have control flow element, which is fun. Conditionally or iteratively adds 0 or more values to the surrounding collection. Okay, this is the part I saw and I really liked so far. So null aware elements evaluates an expression, and if the result is not null, inserts the value into the surrounding collection. Okay. Then we have spread element. Iterates over a given sequence collection expression and inserts all of the resulting values into the surrounding collection. Yep. So just like spread operator in JavaScript, for example. Then we've got the null-aware spread element, similar to the spread element, but allows the collection to be null and inserts nothing if it is. Okay. Yep. Okay. And then if element conditionally evaluates an inner element based on a given condition expression and optionally evaluates another else element if the condition is false. Okay. So yeah, I really like that concept of just having if statement within the collection literal, just so that, you don't have this additional code. Because something that is written very often is, let's say that we want to create some kind of record, right? Let's say, I don't know, employee or something. So var employee, and we're just gonna say that it's gonna be a record type or something. So we're gonna create a record and it has, let's say, named parameters, right? So we'll have name. Name is not ban. Okay. Uh, Wait, I actually need to make this a string. Sorry. And then let's say another one will be. Wait, do I need to do it this way? No, I don't have to. I think name will be not ban, and maybe age will be. I don't know, 9,000, right? And we finish it here. And it's unhappy because of something. Unidentified name. Oh, because in here we just don't have to do that. If we give it a name, it already is a named one. Okay, great. So this, I guess, would work, right? But then let's say you're creating that and then, you will have if, and this won't even work here because we would need to define that this can be something else. So let's say that salary, right? We're gonna say that is no, or let's just say 0 for now. And then if something, right, is whatever true, then we're actually gonna see, what, odd employee dot salary is whatever, negative 100. Okay, that in theory should work. Their salary isn't defined. Oh, of course, because we're dealing with records now, so we can't set it. But let's imagine that this is a class, right? We will be able to set it afterwards because of our if statement. But now this means that I can do if something is true. I don't know how to format it, but I assume it will be minus this, else whatever 0, right? And we can just set it this way. Of course, here it's not happy, but in some way in collections we could do that. So yeah, we'll get to decent examples at some point. And then we have for element, iterates and repeatedly evaluates a given inner element, inserting 0 or more resulting values. There we go. To learn more about collection elements, see the following sections. Okay. So it looks like we're going to go over every single one of those. Yep. So let's start with the most basic. An expression element evaluates a single expression and inserts the resulting value into a collection. This expression can encompass various constructs like literals, variables, operators, function calls, and constructor calls, right? An expression element has the syntax in a collection. Expression. So the way I understand it is, let's go with an example that actually works, right? Let's say we created some kind of a game that has bunch of different parts of functionality like modules that can be loaded or unloaded, right? So let's say var game mods, right? Let's say these are some mods for a game, and that's a list, okay? And in that list we just put names in, right? So we have a list where we have, the base of the game. So we have the base mod, and maybe we have, let's think about something like Factorio. Maybe we have extra belts, right? And maybe another one which will be, I don't know, uh, squeeze through or whatever the name of the mod was, right? And this way we have 3 expressions. So this evaluates to something that produces a value. So I could, in theory, do extra plus belts, right? This is an expression that produces a value, therefore it will be evaluated and just works. So we do mods, will be printed, and we'll see that we have base, extra belts, and squeeze through, right? There we go. So next we have map entry elements. And map entry elements evaluates a pair of key value expressions and inserts the resulting entry into collection. Both the key and the value within a pair can be expressions. Yep, so we have very similar, it's just we have some expression here, colon, an expression here. So that way we can actually evaluate something here and actually evaluate something here. So this is evaluable inside the, what they call it, literal, which is quite nice because very often those keys already need to be, static in so many languages. So it's nice that we can actually do it a fancy way. So we could do var mapping, right? And we say that it's a map. And this map will be, let's say, from, base mod is whatever, v1 or something, right? And then we could do, let's say that the extra plus belts, right? We can actually do that is I plus don't. No. Okay. Just put a space here. And we have both actually evaluated. So it's very nice that the left side is allowed to be this way. This is really, really cool. Okay. So, but other than that, it's straightforward. So now we have null aware elements. And null aware elements evaluates an expression, and if the result is not null, inserts the value into the surrounding collection. So, this is quite a new feature. A language version of at least 3.8. Do we have, what's the current language version? 3.8. So that's the newest feature. It was just added. The null aware elements. There we go. Brand new. So what do we have here? A null aware element has the following syntax. Oh, we just put a question mark in front of it, and that's it. Okay, a null aware element has the following syntax for a map entry. So we can do that. So the key actually has the thing. The key is a null aware element. So therefore, if this evaluates to null, I guess we don't do the whole thing. Value is null, a null aware element. So this will be the value all or the null. Wait a moment. Null aware element evaluates an expression, and if the result is not null, inserts the value into the surrounding collection. So in this case, I guess if the left side evaluates to null, it will just not insert the whole thing. Here, if the value evaluates to null, entire thing doesn't get inserted. And here, if any of those left or right evaluates to null, it's not gonna get inserted. Okay. Key and value are null aware elements. All right. In the following example, the result for the null aware element question mark A is not added to a list called items because A is null. Exactly. Absent value, present value, because this one evaluates null, right? So be like, oh, it's null. I'm not gonna answer that. So just skips that, which is awesome. And the same thing here. It's just this one has value, so it's gonna be present. And if we have a question mark, we just literally inserted the null value. So yeah. Okay, I like that. So in this case, could be, question mark, get whatever, turds on, right? And if this return null, it would just not insert it. Okay. So we can say return type would be string question mark, right? And this will be get turrets mod. And we can say that it will be return null. And this is not happy. Because string is coupled, right? There we go. Now it should evaluate to the point where we will have, the third mod won't show up. It will be just empty, right? But if I would do this, I think it will actually put in the null in here. See? But if we're gonna put the question mark back, but return a value, I don't know, 3 or something, run, we have the third value. Okay, that's great. I really like that. The following example illustrates various ways that you can use null-aware elements inside a map entry. So this is fun. Okay. So present key is apple, absent key is null. Present value is 3, absent value is null. Okay. So if we have items where present key and absent value are without question marks, it's gonna insert it. Okay. But if we're gonna do question mark absent value, in this case, oh, this evaluated to null, I'm not inserting anything. So it's just an empty. The same goes here. If we have just this be null, it's not gonna insert anything. And here we have absent key and absent value. But what if we had one of those? Huh. So I want to test that. So let's do something like absent key. I mean, I don't have to do that, right? Or no, let's do that. Absent key will be null. Existing key is gonna be string key. And then we have absent value and existing value. There we go. And then we're gonna do this thing items, right? And we're gonna print items f. Hopefully that's gonna be fine. So if I'm gonna do this, in this case, they're both empty. So it's gonna be one giant empty. There we go, empty map. But what if I'm gonna say that, hey, absent key, or let's do actually existing key, right? So this one should provide a value, while this one should be empty. What's going to happen? Empty, right? So if any of those is empty, so let's do absent key, but existing value. Run. There we go. We have empty. Only if we have existing key and a value, it's gonna actually work. There we go. All right. What if I'm gonna put a colon in the name? How is it gonna print it? So I could do key is hello, comma, space, other key, run. It's gonna look as if I had 2 elements. Oh no. Don't trust the print to actually tell the truth. Okay. So next we have spread elements. The spread element iterates over a given sequence and inserts all of the resulting values into the surrounding collection. Okay? The spread element has the following syntax in the collection. The sequence expression can represent any expression that evaluates to an object that implements iterable. Okay. So we have the mention of iterable. That's great. So we just do 3 dots and then we have our expression. So in the following example, the elements in the list called A are added to a list called items. Just like that. We have A, which is 1, 2, null, and 3. And if we're going to spread them in between those, there we go. It worked. We are spreading an expression that might evaluate to null, and you want to ignore the null and insert null elements, use a null-aware spread element, which we'll be talking about in a second. To learn more about the spread operator, read up. Okay. So the null aware spread element is similar to the spread element, but allows the collection to be null and inserts nothing if it is. A null aware spread element has syntax in the collection. So we just throw in an extra question mark. So in the following example, a list called A is ignored because it is null and the elements are called. Okay, so this is null, right? So B is fine. And if we're gonna do items, we're gonna create list with A and B. In this case, should have 0, then you should have nothing, and 1 null, 3. There we go, and the 4 at the end. There we go. But elements in a list called B are added to a list called items. Notice that if a collection itself is not null, but it contains elements that are, those null elements are still added to the result. There we go. So is there a way to quickly filter them out? Because of null safety, you can't perform a spread operation on a value that might be null. The following example produces a compile time error because the extra options parameter is nullable and the spread operator used on extra options is not null aware. Exactly, because this won't work, right? Because it is nullable. Therefore, we would need to throw in that question mark here. If you want to spread a nullable collection, use a null aware spread element. Yep, we just threw in a question mark and it's all happy. Okay, so I guess we don't have like a quick filtering, at least now. So let's move to if elements because this is fun. So if elements. An if element conditionally evaluates an inner element based on a given condition expression and optionally evaluates another else element a condition if the condition is false. So I mean this is kind of like hello Super Duckling Boy on Twitch. Spread operation is 3 dots, so you can do ... items exactly. That was probably posted a long time ago, so sorry for being behind. Yeah, we're done with the spread. Yeah. Okay, so yeah, I mean it's not the same as the ternary operator, so like in the JavaScript, because it would still return a value that gets inserted into the list. In this case, the element is not inserted at all, as if that entry wasn't there. So the if element has a few syntax variations. So if the bool expression is true, include the result, right? So if you have the expression and the result. If the expression matches the pattern, include the result. So if expression, case, pattern, result. That's interesting. That's very interesting. With the case word. If the operation resolves as true, include the first result, otherwise include the second result. So we have more of a ternary thing, right? This is the equivalent of a ternary, where we always insert some kind of value. It just depends on which one. So going on with our example of the game mods, we could have something like if 2 is 2, then we will insert the whatever true math mod. Okay, so when we run it, let's just ignore this crazy stuff. I'm gonna run it and it should be, yep, include the true math. But if we were saying something different, it just doesn't include it because it doesn't. So this would be good if 2 is equal to, we input the true math mod, else it will be the bad math mod. Okay, there we go. Something more fun will be, let's say if 1 is equals 2, we include math fix mod. Okay, but the math works, so we don't include it really. Okay, great. So this one is gonna be interesting. This is the if else, and then if the operation resolves as true, includes the first result, otherwise. So this is the same thing, but with this expression case pattern. So the following examples illustrate various ways that you can use an if element inside of a collection with a Boolean expression. Okay. So yeah, items is this, that, and that, and that. And therefore, by flipping that, you can either add that element or not add it, which is awesome. And include item, if not include item, this. Okay, great. Yep, because it's an expression, this can be more here than just one thing. And here you have actual comparison, right? Great. And here we have the if name is kiwi, we return 1. Otherwise, if, okay, so we're nesting them, name is pear, we do 10. And therefore, if it's neither kiwi nor pear, nothing's gonna get added, right? Because we put an apple, so this element was skipped. Okay, that's a nicer case of having the else. That makes sense now. Great. The following examples illustrate various ways that you can use if element with a case part inside collection. So what is this? So if data case int I. Okay, so data is integer and we export it as an I to use it within the actual value on the right. Great. So this is to match a pattern. In this case, the pattern is string, bool, or double, right? Otherwise, we can say word case string and length is oh, I see. This is where shenanigans starts to happen. So we created a list of element 1, something, and 3. And that something is if the word is of type string, then we already matched the pattern, right? But we export the length of that word as the variable word length. So we can actually put it in here. But why? I need to test this one because I wonder if this is due to how code is compiled. So we have this here, right? This exact same code. Items, and we can just do print items. We're gonna run it. And we have 153, right? But what if instead of doing this whole thing, I just said, hey, case string, right? Can I do word length dot, word dot length? In theory, it should be fine, right? Run. Oh, 153. Okay. Do I need to do this like extracted number, like S, for example, string S? That was fine. It's just, okay, so it suggests that I can do this too if I don't want to use the S specifically, right? And here I can do word length because it allows me to. But what if I'm gonna say this is an object? Okay, I'm gonna say explicit, this is an object. It works no problem. So I can call, so the way I understand it is that the moment we pass this if for the word, suddenly it treats that the word is not an object but actual string. Because I would understand, string word, right? So I can do string word or length. So I actually casted it properly here. Because I could do if word case integer, right? So int word. I could say, hey, instead of that, we need some kind of number. We're gonna do int word plus 2. And in theory, that's fine, but it's just gonna not work because we have a string. But what if I'm gonna do this now, where I just do word.length? Oh, now it's unhappy. Sorry, the getter length isn't defined in type object. So the other time it was kind of smart enough to figure out that there's no other option. Now we have other options, so we need to use this. Okay, makes sense. Therefore, this is a poor example, but I guess if we went, oh, I see, we could probably extract multiple out of there. That's something that we'll probably learn when we get to something like patterns down here. Okay. And Super Duckling Boy says you can also write that like this, by the way, for clean syntax. Oh yeah, the Turner expression, yeah. Yeah, some of those I could write that way. Yeah. As in if else. But that's in cases where it will always return a value. But if we want to have a situation like this, where we don't want to return anything, we can't use the Turner expression. So then we have order details, apples. Okay, so we're step up to maps, and we can have the case expression. Wait, what? No, this is just a list. Okay, so it's still a list. Product order details, and if this matches the pattern where we have element of anything, then we have an integer, and then anything, we're just gonna do that. But if otherwise we have anything, and an empty string at the end, we have this. Otherwise, deliver in progress. Okay. Yep, this is where pattern matching starts to come in with this case where, like, oh, I can actually do some more complicated stuff. And that could be fun with maps and possibly records. No, probably with lists. Yeah. Okay. Can mix different if operations with an else if part. For example, if A is apple, 1. Otherwise, if A is case mango, yeah, we can just mix and match them so we can do case on the right or something like that. It's all fine. On the left, well, no case on the right. Whatever. Yep. Okay. And we can actually, okay, so with the case, we can just do the comparison normal. So we'll need to learn more about this pattern matching with the case word to get more out of it. Definitely. To learn more about the if conditional, see the if statement. To learn more about the if case conditional, see the if case statement. Okay. And that leads us to branches. It'll be probably in control flow branches where we'll learn more about loops and if statements. It's funny how we learn all this pattern matching within lists and other crazy stuff before we even properly learn about if statements, loops, or basic patterns, right? It's very interesting. Okay, so let's finish off with four elements because this is really powerful in my opinion. A for element iterates and repeatedly evaluates a given inner element, inserting 0 or more resulting values. So a for element has the syntax in a collection. So for, some expression in a collection, and result. Otherwise, for initialization clause, semicolon, conditional clause, semicolon. Excuse me, I'm getting sleepy. Increment clause. And the following examples illustrate various ways to use it inside a collection. So yeah, we can say items 1, then we have 4 var n in numbers, and we return that number basically to its own power. Squared. Not to its own power, just squared. So yeah, in this case, we're gonna have element 1, then we're gonna have iterate over those numbers. So it'll be 2 to the power of 2. There we go, 4. And then it will be 3 to the power of 3, 9. 4 to the power of, I mean, 4 to the power of 2 is 16. There we go. And then at the end we have our 7. So yeah, this is a fun little for loop. I like that. So in our example, we could say that after we did math fix, potentially we can do something like for, I don't know, let's say we have for DLC, yeah, DLCs, which will be a list of, I don't know, what DLCs could be here. DLC 1, DLC 2, and DLC 3. It's just I'm missing these. Okay. And there we go. We have our DLCs. So we could, in theory, say for DLC in DLCs. Wait, do I need a var in there? Yes. And we just return DLC. Sure. So when we run it, we'll see that we added all the DLCs, right? But we could do more stuff, which is, DLC, bam, bam, and we have actual strings like that, which is very confusing when we print it. So there we go. And we could actually, in theory, just do 1, 2, and let's say 4 because we skipped the 2. Oh, and no. Now we need to string. Will that work? Yes, there we go. The C1, 2, and 4. Great. That's how we can do it. So we have, okay, a for loop that counts down. Okay. We have a for loop that counts up. Great. To learn more about the for loop, see the for loop. So this would be probably interesting if we were able to make some of those elements conditional as well. So the nest control flow elements. There we go. You can nest control flow elements within each other. This is a powerful alternative to list comprehensions in other languages. In the following example, only the even numbers and numbers are included in items. So we have, oh, there we go. If n is even, n. There we go. So we can say that we have DLCs 1, 2, 3, 4, and 5, right? Maybe 6. And here we want to do something like if the DLC is not 3, right? We return that. So we should actually skip the DLC number 3. There we go. Just like that. It looks ugly, but in theory, you could just, we're making a final thing. So each item is some kind of important thing where you could actually do some filtering with this if statement, right? On a list. And you can do it in a new line. So we just plop it here. And there you go. Because you don't need any brackets around it. Yep. So we run it, it still works. Great. It's common and idiomatic to use a spread on a collection literal immediately inside of an if or for element. For example, so we create items. If condition, one thing. If condition, and we do spread operator, multiple things. Okay. So that will insert a list of one thing, and inside of here we have Nested list. Oops. Um, okay. So what did the spread operator do? Nothing. Oh, multiple returns element like this, and things is just one thing. Okay, very confusing example, but sure. It's nice that we can basically give it a condition, and if that, then actually insert multiple elements, which is great. Okay. You can nest all kinds of elements arbitrarily deep in the following example if for and spread elements are nested within each other in a collection. So we have the nest items set to true, ys, I don't know, years or something, is 1, 2, 3, 4. So we create a list items. If nest items, so if true, then this is going to return. So we know that we're going to return it. So the spread operator of this list. And this list has a for loop inside. So for values from 0 to 2, okay, so we have 3 elements. We iterate over them. And then we have y. Oh, for all the y's in y's. So we have 4 elements. And then if the x is larger than y, I mean smaller than y, then we combine them times 10, and there we go. And somehow we went through, oh dear, 3 times 4, 12 cases, from which we selected just several of them. Okay, very strange example, but there we go. Okay. All right. I like that. It's, I guess, rather clear for now. We'll see how often we actually use that, but I love the ability of if and for inside of those collections. Literals, so that's great. Okay, so looks like the topic of generics is very short, so I think we should be able to go through that today. I'm a little bit low on stamina, did a lot of work today, so I guess it'll be a little bit shorter today. Okay, so let's look at generics. If you look at the API documentation for the basic array type, list, there we go, list E class. You'll see that the type is actually list E. The angle brackets notation marks list as a generic or parameterized type, a type that has formal type parameters. By convention, most type variables have single letter names such as E, T, S, K, and V. E. I guess E as in for an element. That's why I guess the E was given, because normally is the T for type, but I can see that E for element. I mean, I guess this is by convention because you can still give it more descriptive name if you want to. So here, looks like some people need convincing to why to use the generics. Generics are often required for type safety, but they have more benefits than just allowing your code to run. Properly specifying generic types results in better generated code. You can use generics to reduce code duplication. Exactly. The second part is awesome. If you intend for a list to contain only strings, you can declare it as a list of strings. Read a list of string. That way, you, your fellow programmers, and your tools can detect that assigning a non-string to the list is probably a mistake. Here's an example. So we define names as a list of strings. Names, add all. We try to add those. Great. We're gonna try to add a number. We'll be like, oh, sorry, I don't think you wanted to do that. Number is not a string. Another reason for using generics is to reduce code duplication. Generics let you share a single interface and implementation between many types, while still taking advantage of static analysis. For example, say you create an interface for caching an object. Abstract class, object cache. It just returns an object, get by key, you give it a string key, and then a set by key. And you set it, right? You put an object here. You discover that you want a string specific version of this interface. So you create another interface like, oh, string cache. Okay, so that you don't need to constantly convert between string and object whenever you put some stuff in and take out. Later, you decide you want a number specific version of the interface. You get the idea, right? We just keep adding more specialized, like end cache, or maybe then we need some kind of employee cache, right? It's all get by key, set by key. The only thing that changes is those two fields where this is string, this is object, maybe an integer, right? Generic types can save you the trouble of creating all these interfaces. Instead, you can create a single interface that takes a type parameter. So abstract class, cache of type T. And then we just put, hey, this is a T and this is a T. So whatever we define as this will be the type that gets saved or read, right? In this code, T is the stand-in type. It's a placeholder that you can think of as a type that a developer will define later. So using collection literals. List, set, and map literals can be parameterized. Parameterized literals are just like the literals you've already seen, except that you add type for the list and sets, or key type and value type for maps before the opening bracket. Here's an example of using typed literals. So we create a map of strings. We explicitly say, hey, strings only. Unique names. Again, this is a set of explicitly strings. And we have a map where key is a string and the value is the string. Therefore, we can put an integers either as keys or values. Next, using parameterized types with constructors. To specify one or more types when using a constructor, put types in angle brackets just after the class name. For example, name set, right? So we use the class name set and then the type of string. So this will be very similar to how we defined it, right? Name of the constructor or whatever, and type T. Yeah, there we go. And we have off, right? Because that's the actual constructor. So yeah, there we go. Following code creates a display tree map that has integer keys and values of type view. There we go. Generic collections and the types they contain. Dart generic types are reified, which means that they carry their type information around at runtime. For example, you can test the type of a collection. So names is a list of strings, right? Names add, blah, blah. And then print name is list of strings, and it will say true. So the thing is that this is because when we define a list of something, it kind of that instance holds the info that, hey, I'm a list of string. And therefore, yeah, we can check that value later. In contrast, generics in Java use erasure, which means that generic type parameters are removed at runtime. In Java, you can test whether an object is a list, but you can't test whether it's a list string. Oh, interesting. In C#, all the types hold their metadata. You can actually access the metadata to programmatically read all the things about the type and its parents and whatever, the whole tree. But that's so-called reflection system, and many program languages have that, or they have that implemented on top of through some other means. Okay, restricting the parameterized type. There we go. When implementing a generic type, you might want to limit the types that can be provided as arguments, so that the argument must be a subtype of a particular type. This restriction is called a bound. You can do this using extends. A common use case is ensuring that the type is non-nullable by making it a subtype of object instead of the default optional object. There we go. Class foo t extends the object. Any type provided to foo or t must be non-nullable. There we go. You can use extends with other types besides object. Here's an example of extending some base class so that members of some base class can be called on an object of type t. So class foo and t extends the some base class. There we go. And yep, class extender extends some base class. Yeah, therefore we could create instance of class foo by providing the extended, right? Extender. There we go. It's okay to use some base class or any of its subtypes as the generic argument. Yep, but you won't be able to provide an integer or something else. Therefore, because you use the base class, you can call the stuff from the base class somewhere in the implementation. Okay, it is also okay to specify no generic argument. Okay, so by default, it will revert to the base class. Okay, otherwise to probably an object or nullable object if it's not bound. Okay. Then we have specifying any non-sum base class type results in an error. There we go. You can't do that anymore. Then we have self-referential type parameter restrictions, the f-bounds. When using bounds to restrict parameter types, you can refer to the bound back to the type. You can refer the bound back to the type parameter itself. This creates a self-referential constraint, or f-bound, for example. So, if abstract class interface, some comparable of type T, where we can basically say, hey, compare to that type T, right? So it's an interface, so various types can implement it, right? So that we can implement comparison to some other types. And integer compare and offset, it takes T, type T that extend comparable T. Okay. So suddenly we have the situation where our type that we want to put into compare and offset extends the comparable of the same type. So this is for compare and offset of types that are comparable to themselves. Therefore, we have type, the same type of 1 and 2, and therefore we can compare them to each other because they are comparable to each other. Okay. Kind of hard to think of at the very moment when you're reading it, but when you're writing the code, you're like, oh, I need to do something like that, and it's obvious at that point. Class A implements comparable A. Okay, override compare to A other. Excuse me. So yeah, we basically specify a class that is comparable to itself, right? So I can compare two instances of the same class, and we provide the implementation of it, and therefore we can properly use the compare and offset by providing two instances of the class. There we go. The f-bound T extends comparable. T means T must be comparable to itself, so A can only be compared to other instances of the same type. And using generic methods, there we go. Methods and functions also allow type arguments. T first, so we have the function first that returns T. So of type T, which returns that type, but it also takes in a list of those of this type. So we do some work and we just return that first element of the list, right? So this literally does, uh, hey, return me the first element of the list, just in the form of a function. So therefore we provided a list, and all those generic shenanigans mean that the compiler will figure out that, oh, if you put in a list of integers, that means you're going to return a single integer back. Here's the generic parameter of the generic parameter on first allows you to use the type argument t in several places, in the function's return type, in the type of an argument, and the type of the local variable. There we go, because we also created the local variable here. Great. Okay, let's just breeze through the type defs, and type system is a bit longer. I'll see if I'll manage. Because in theory, we're not even at the 2 hours mark. I'm just really thirsty. Okay. So type defs. A type alias, often called a type def because it's declared with a keyword type def, is a concise way to refer to a type. Here's an example of declaring and using a type alias named intList. Type def intList is just a list of ints, right? And therefore, instead of everywhere writing list int, you can just use this instead, right? I mean, this is kind of a silly example, but when you get to larger, more complex things that you reuse all over the place, type def is awesome. That's something I wish C# had. A type alias can have type parameters. Type def list mapper. Oh, so we can actually still have it generic somewhat. So list mapper is X and it's a map. There you go. It's a map where key is of type X and it holds a list of values of type X. So therefore we can say that, hey, either M1 is a map of string and list of string. It's very verbose, especially when repeated over the place. Or you just do a list mapper of string and it just replaces this with that. And at the end of the day, this is a little bit easier to understand once you understand what the software is doing. Version note, before 2.13, type defs were restricted to function types. Using the new type defs requires a language version of at least 2.13, which is a long time ago. We recommend using inline function types instead of type defs for functions in most situations. However, function type defs can still be useful. Like type definition, compare of t, right, we'll call that, is function that takes those two t arguments and returns an integer, right? And we just write this function, therefore we can say that sort is compare int, and it's true because this function fits this type. Okay, it's good that we can actually do those things, those comparison. That's very helpful. Okay, that was simple. I like that. It's just so far we have nothing indicating that this type definition, let's say, can be used from, because when you're working on a code base, you often have multiple files, right? Can I use this throughout multiple files? Or do I have to redefine it for each file to just have it helping out? Because I don't remember where in some language there was a situation where you can define those type of definitions, those aliases. They're only within a single file. You can't reuse them anywhere else, which kind of sucks. Okay, next, the Dart type system. The Dart language is type safe. It uses a combination of static type checking and runtime checks to ensure that the variable's value always matches to the variable's static type, sometimes referred to as sound typing. Although types are mandatory, type annotations are optional because of type inference. One benefit of static type checking is the ability to find bugs at compile time using Dart's static analyzer. You can fix most static analysis errors by adding type annotations to generic classes. The most common generic classes are the collection types list T and map KV. Go. For example, in the following code, notice that here is list of type T, while definition was specifying it's a list of type E for element, while here we have KV for key and value. For example, in the following code, the print integers function prints an integer list, and main creates a list and passes it to print ints. So we will have failure, right? Print integers expects a list of integers, right? So we have empty list, we add 1, and we try to add a string too. So this should already kind of fail. But let's imagine that it didn't fail because we made because we already defined it like this. So this will define an empty list of objects. Therefore, we can add whatever we want inside. And then when we try to pass it here, it's like, oh, sorry, we can't accept a list of objects. We need a list of only integers, and this will fail. The preceding code results in a type error on list highlighted above at the call print integers. Error. The argument type list dynamic, so this just calls list dynamic, can't be assigned to the parameter of type list integer. Argument type not assignable. I hope we're going to learn more about this dynamic keyword and how it really works. How does it differ from something like an object or nullable object? Does it mean it accepts other things than those two? Don't know. The arrow highlights an unsound implicit cast from list dynamic to list integer. The list variable has static type list dynamic. This is because in the initializing declaration, the var list, an empty list, right, doesn't provide the analyzer with enough information for it to refer a type argument more specific than dynamic. The print integers function expects a parameter of type list integer, causing a mismatch of types. When adding a type annotation, integer, on creation of the list, highlighted below, there we go, right? We defined it as a list of integers. The analyzer complains that a string argument can be assigned to an integer parameter, right? I mean, here, right? Because here it's fine. So removing the quotes in the list add and the string 2 results in code that passes static analysis and runs with no error warnings, right? Because here we were trying to add the string 2 that contains the character 2, and that was not good. Here it's fixed. It's an actual integer, so this is happy, and therefore we can pass it to our list. What is soundness? Soundness is all about ensuring your program can't get into certain invalid states. A sound type system means you can never get to a state where an expression evaluates to a value that doesn't match the expression's static type. For example, if an expression's static type is string, at runtime you are guaranteed to only get a string when you evaluate it. Dart's type system, like the type systems in Java and C#, is sound. It enforces that soundness using a combination of static checking, compile time errors, and runtime checks. For example, assigning a string to int is a compile time error. Casting an object to a string using an as string fails with a runtime error if the object isn't a string. So then we have the benefits of soundness. A sound type system has several benefits, revealing type-related bugs at compile time. Like a sound type system forces code to be unambiguous about its type, so type-related bugs that might be tricky to find at runtime are revealed at compile time. More readable code. Code is easier to read because you can rely on a value actually having the specified type. In sound Dart, types can't lie. More maintainable code. With a sound type system, when you change one piece of code, the type system can warn you about the other pieces of code that just broke. And better ahead of time compilation. While ahead of time compilation is possible without types, the generated code is much less efficient. Here the compiler knows what the type is supposed to be, therefore it can skip some checks and whatnot because, it's guaranteed that it's gonna get a proper value. Tips for passing static analysis. Most of the rules for static types are easy to understand. Here are some of the less obvious rules. Use sound return types when overriding methods. Use sound parameter types when overriding methods. And don't use a dynamic list as a typed list. Let's see these rules in detail with examples that use the following type hierarchy. So we have some hierarchy of animal, and then we have alligator, cat, and honey badger. And cat has further specialized classes like lion and Maine Coon. Okay? The sound return types when overriding methods. The result return type of a method in a subclass must be the same type or a subtype of the return type of the method in the subclass. Oh, I love those. They're just like, wait, what? I need to reread that. The return type of a method in a subclass must be the same type as subtype of the return type of the method in a subclass. I'm sorry, this is just silly. Consider the getter method in the animal class, right? Like animal class, we chase animal and animal get parent. So the parent is a getter that returns an animal, right? The parent getter method returns an animal. In the honey badger subclass, you can replace the getter's return type with honey badger or any other subtype of animal, but an unrelated type is not allowed. So we do honey badger extends animal, and when we override the parent, we can specify that it always returns a honey badger for some reason, right? Because this is a specialized class, right? So it can actually guarantee that, you know what? The parent of a honey badger will be always a honey badger. It won't be other generic animal, which would in theory allow you to assign a cat or an alligator to be a parent of a honey badger, right? Wouldn't make sense. Here we can do that. But if we're gonna specify that we're gonna use root, whatever root is, then it's gonna be unhappy, right? In my case, root. I don't know, root. But if we were probably try to specify cat as a parent, it wouldn't work. Use sound parameter types when overriding methods. The parameter of an overridden method must have either the same type or a super type of corresponding parameter in the superclass. Don't tighten the parameter type by replacing the type with a subtype of the original parameter. Oof. If you have a valid reason to use a subtype, you can use the covariant keyword. Okay. So consider chase animal method for the animal class. So we have animal and we have the chase. You can chase another animal. So the chase method takes an animal. A honey badger chases anything. It's okay to override the chase method to take anything as an object. So we can say chase object, right? So we can kind of loosen it up because that still holds the contract that when we can pass animal to it from some other place, because this whole hierarchy means that you can just say that something is an animal, or really you're holding the badger, and you will still be able to pass the animal objects inside of it, the chase, even though you're calling this one really that could in theory take an object. So yeah, the following code tightens the parameter on the chase method from animal to mouse, subclass of animal, right? So we have class mouse, which is from the animal, right? And the cat extends where it can chase a mouse. And this is a problem because suddenly if you have a cat instance dressed up as generic animal, you can, type system would allow you to just plop in a honey badger here, right? But this wouldn't, in theory, would create a conflict because suddenly it's like, oh wait, honey badger is not a mouse. So that's that part. This code is not type safe because it would then be possible to define a cat and send it after an alligator. So we create a variable animal, so we hold an animal. We create a cat, but it will be still accessible just as a type animal. And therefore, the chase defined on animal allows to put any animal here. And therefore, you know, we can pass an alligator, which conflict here. So that's why we aren't supposed to do that. Don't tighten those tabs on the methods. Don't use a dynamic list as a typed list. A dynamic list is good when you want to have, when you want to have a list with different kinds of things in it. However, you can't use dynamic list as a typed list. This rule also applies to instances of generic types. The following code creates a dynamic list of dog and assigns it to a list of type cat, which generates an error during static analysis. So create a list of cats, right? And we pass in a dynamic list in here of dogs. And that will be sorry. Whenever you have dynamic, we can't trust whatever is inside, so this just says no. But if we had dynamic list and try to put dynamic stuff inside, it's gonna be okay. Yeah. Okay, runtime checks. Runtime checks deal with type safety issues that can be detected at compile time. For example, the following code throws an exception at runtime because it's an error to cast a list of dogs to a list of cats. So we have animals and a list of dogs. And we just say animals, we try to cast it as a list of cats. And it's like, during runtime, it's sorry. This is a list of dogs. It won't work. So yeah, that's during runtime. Implicit downcast from dynamic. Expressions with a static type of dynamic can be implicitly cast to a more specific type. If the actual type doesn't match, the cast throws an error at runtime. Consider the following assume string method. So we have assume string that returns an integer but takes in a dynamic object. So then we create a string. String is the object. Check at runtime that object is a string. Okay, so we're gonna try to do that because this is, I guess, allowed during compilation because this is dynamic. Therefore, it will be the same as object as string, right? Therefore, it will be an error. Sorry. This thing might have been something else. In this example, if object is a string, the cast succeeds. If it's not a subtype of string, such as int, a type error is thrown. There we go. To prevent implicit downcasts from dynamic and avoid this issue, consider enabling the analyzer's strict casts mode. Okay, so you can just do strict casts. I guess you will need to then use the as keyword by yourself. Okay, I like that. To learn more about customizing the analyzer's behavior, check the customizing static analysis. Okay. Let me just check the comments. No comments. Nobody's watching. Oh well. Type inference. The analyzer can infer types for fields, methods, local variables, and most generic type arguments. When the analyzer doesn't have enough information to infer a specific type, it uses the dynamic type. Okay. Okay, so it will default to dynamic whenever it's very confusing. Okay. Here's an example of how type inference works with generics. In this example, a variable named arguments holds a map that pairs string keys with values of various types. If you explicitly type the variable, you might write something like this. Map string of optional objects. Okay? Nullable objects. And we can just assign it and it's all good. Alternatively, you can use var or final and let Dart infer the type. In this case, it inferred it as an object, but not a nullable because we didn't have a null. Okay? The map literal infers its type from its entries, and then the variable infers its type from the map literal's type. In this map, the keys are both strings, but the values have different types, string and int, which have the upper bound object. So the map literal has the object, so does the arguments variable. Yep, there you go. Field and method inference. Okay, we're halfway through. Oof. After that, we're definitely stopping. A, this is a lot of data to process. B, my throat won't take it. Field and method inference. A field or method that has no specified type and that overrides a field or method from the superclass inherits the type of the superclass, method, or field. Okay. A field that does not have a declared or inherited type, but is declared with an initial value gets inferred type based on an initial value. Okay, makes sense. Static field inference. Static fields and variables get their types inferred from their initializer. Note that inference fails if it encounters a cycle. That is, inferring a type for the variable depends on knowing the type of that variable. Yep. And then we have local variable inference. Local variable types are inferred from the initializer, if any. Subsequent assignments are not taken into account. This may mean that too precise a type may be inferred. If so, you can add type annotation. So something like this will fail because here it figured, oh, this is an integer, but then we try to put in a double in there, right? So if we're gonna define it ourselves, we can hold integer and then switch it to a double. There we go. Type argument inference. Type arguments to constructor calls and generic methods invocations are inferred based on a combination of downward information from the context of occurrence and upward information from the arguments to the constructors or generic method. If inference is not doing what you want or expect, you can always explicitly specify the type arguments. So let's say list of integer, we just do that, and therefore this is gonna be a list of integers. Inferred as if you wrote double 3, right? So this is inferred. Okay, we've got a double element, that means it'll be a list of doubles. And here, integer list of double, right? So we've got that list of doubles. And we map it where x is to integer. So it's inferred as iterable of integers, okay? Because it returns some kind of iterable. Probably it's a list, but we don't know. Okay. In example, x is inferred as double using downward information. The return type of the closure is inferred as integer using upward information. Dart uses the return type as upward information when inferring the map method's type argument, which is integer, right? Figured out that, hey, the map is on integer. And inference using bounds. Again, inference using bounds requires a language version of at least 3.7. Okay, this is again fairly new. With the inference using bounds feature, Dart's type inference algorithm generates constraints by combining existing constraints with the declared type bounds, not just best effort approximations. This is especially important for f-bounded types, where inference using bounds correctly infers that in the example below, x can be bound to b. Without a feature, the type argument must be specified explicitly. So class A, where x extends. Wait, what? Where did the x come from? So okay, so what? Oh wait, we have class A and we have the generic type X, right? The stand-in type X, which extends the class itself. Okay. Okay, so it can be class A with a type of class A or any of the subclasses. Okay, sure. Therefore, class B extends A from B, right? So that's gonna be fine. C extends B. That's again great. It's the same thing. Void. So we have function that returns void. And it takes X that extends A of X, right? And we provide it here. So that's good. And when we call it, hey, B, we create a B and we call the function on B. It automatically infers that it's fine because we don't have to specify that, oh, this is a B that extends this and that. Okay. Without using bounds, inference relying on best effort approximations would fail after detecting that C is not a subtype of A of C. Okay. I see, because this would assume that it's A of C, but not in this case. All right. Okay. And there we go. This is very explicit. Alrighty. Here's a more realistic example using everyday types in Dart like integer or number. So we have a function max that returns x. The x extends comparable x, okay? So the max basically takes in those two, let's say numbers, right? Probably numbers. And we just make sure that both of those types can be compared to each other, right? Because we're using the compare to. And therefore we will return the number that is actually larger one. And when we do max 3 and 7, so automatically infer that they are integers, right? Or as number inferred as number 3 and 7 with a feature. Oh, with a feature. Without a feature, it would actually fail. Huh, interesting. As good as implies because this is rather common. With interference using, I mean, this is a complex topic that I don't think anybody needs to be worried about now that it happens automatically, right? Dart can deconstruct type arguments, extracting type information from generic type parameter bound. This allows functions like f, in the following example, to preserve both the specific iterable type, list or set, and the element type. Before inference using bounds, this wasn't possible without losing the type safety or specific type information. So we return x and y from the function f, where x extends iterable y, and then we have the y itself. Okay. So x is just a list of the y element, right? So we provide a list and we return the list itself and the first element. Okay. Great. That makes sense. So void main, and we can just say that my list and my int, we just give it this. So this will this should in theory the structure the result as list of integer and the integer. Okay. So my end, whatever. Compile time error. Excuse me. My int has type integer. There we go. And the same thing with set. I said union works because my set has a type of set of string. Yep. Without without inference using bounds, my int would have the type dynamic. The previous inference algorithm wouldn't catch the incorrect expression and whatever because it was dynamic. At compile time, it would instead throw a runtime error. Conversely, my set union would be a compile time error without inference using bounds because the previous algorithm couldn't preserve the information that my set is a set. Okay. For more information on the inference using bounds algorithm, read the design document. Okay? Great. We're not going to do that. So now let's move to substituting types. Ooh, when you override a method, you are replacing something of one type in the old method with something that might have a new type and a new method. Similarly, when you pass an argument to a function, you are replacing something that has one type, a parameter with a declared type, with something that has another type, the actual argument. When can you replace something that has one type with something that has a subtype of or a supertype? Yeah, it's a question. When substituting types, it helps to think in terms of consumers and producers. A consumer absorbs a type and producer generates a type. So you can replace a consumer's type with a supertype. Okay. And producer's type with a subtype. Okay. Let's look at the examples of simple type assignments. An assignment with generic types. So I guess the consumer will be, let's say, something, the code that is calling a function, right? Well, a producer would be actually the definition of the function or something like that. So simple type assignment. So we again have the same hierarchy classes. So when assigning objects to objects, when you can replace a type with a different type, the answer depends on whether the object is a consumer or producer. Consider the following hierarchy. Consider the following simple assignment where cat C is a consumer and cat C and a cat is producer. So cat C is consumer because it's the actual whatever instance of that holds the instance, right? So it consumes it. Well, cat, this is a producer because it's a constructor of a cat. So it produced the object, I guess. In a consuming position, it's safe to replace something that consumes a specific type, cat, with something that consumes anything, like animal, right? So replacing cat C with animal C is allowed because animal is a supertype of cat, exactly. We have this more generic box, we can still fit cat inside of it. But replacing cat C with a Maine Coon breaks type safety because the superclass may provide a type of cat with different behaviors, such as lion. Yeah, because we have Maine Coon, it's more specialized than this, therefore we can't fit this generic thing in this specific thing, right? It's like, hey, I want a Maine Coon cat, and you give it any cat, and it's not gonna work. But if you're gonna ask for any cat and you're gonna get a Maine Coon, it's good because Maine Coon is cat. I'm happy, right? In a producing position, it's safe to replace something that produces a type cat with a more specific type, like Maine Coon. So the following is allowed. There we go. You asked for a cat, you got Maine Coon. Great. The generic type assignment. Are the rules the same for generic types? Yes, consider a hierarchy of lists of animals. A list of cat is subtype of a list of animal, and a supertype of a list of Maine Coon. There we go. So in the following example, you can assign a Maine Coon list to my cats, because list of Maine Coon is a subtype list of cat. There we go. List of Maine Coon, right? So list of cats, I can just assign my Maine Coon, that list. What about going the other direction? Yeah, it wouldn't work, of course. I mean, I'm just surprised this goes that much. I don't know. It's kind of intuitive, but hey, maybe somebody learns it from scratch, is not used to generics or doing, something with, subclasses and whatnot in type systems. Maybe it's not so obvious. Interesting. Never thought about it. I guess maybe it was confused to me when I was learning the first time. Might have been. This assignment doesn't. I mean, I remember as a kid, I don't know, I was in sixth grade or something. I was trying to learn types in Pascal. I mean, Object Pascal. And for some reason, I couldn't until a few months later, it just clicked. And oh, okay, I understood. And now it's just really intuitive. Okay, so this assignment doesn't pass static analysis because it creates an implicit downcast, which is disallowed from non-dynamic types such as animals. There you go. To make this type of code pass static analysis, you can use an explicit cast, right? So as list of cat, and then if by accident this isn't an actual list of cats, you're gonna have a runtime error. An explicit cast may still fail at runtime, though, depending on the actual type of the list being cast. There you go. We've got methods. When overriding a method, the producer and consumer rules still apply. For example, this is a consumer and this is a producer. So we have a class where the method is a consumer while because it takes it as an argument, right? While this is a producer because it returns that animal. Okay, makes sense. Getters are producers. Functions that take it and not return it are consumers. So for a consumer such as the chase animal method, you can replace the parameter type with a supertype. For a producer such as the parent getter method, you can replace the return type with a subtype. For more information, see the sound return type when overriding methods and a bunch of other stuff. Okay, so we're finishing off with the fun covariant parameters. Such a scary word, covariant. Some rarely used coding patterns rely on tightening a type by overriding a parameter's type with a subtype, which is invalid. In this case, you can use the covariant keyword to tell the analyzer that you're doing this intentionally. This removes the static error and instead checks for invalid arguments typed at runtime. Okay, so the following shows how you might use covariant. So we have the class animal. It has the chase animal X, right? And then we have the class mouse extends animal. Great. And then we have a class cat extends animal override, and we do void chase, and we actually specify that the cat can only chase a mouse, which is normally like not allowed, but we can ignore that error with specifying it's covariant. But still, if we define it like that, so now static analysis is fine. But if during runtime you're gonna throw an alligator in here, right? Because you held the cat as a variable of type animal, and you're gonna throw in, hey, chase an alligator, you're gonna get a runtime error. Okay. Although this example shows using covariant in the subtype, covariant keyword can be placed in either the superclass or subclass method. Usually the superclass method is the best place to put it. Covariant keyword applies to a single parameter and is also supported on setters and fields. Okay. And we have other resources. The full resources have further information on Sound Dart, so fixing type promotion failures, sound null safety, and customizing static analysis. Oof, okay, we got through it. Yeah. So next time we'll talk about patterns, and looks like there'll be a lot to talk about, because this is just overview and usage. We have pattern types, which is a lot. Apply tutorial, and then we will finally have loops, branches, error handling. Okay, but yeah, this was a nice overview of types. It kind of gives the idea of what the language feels like and how to deal with that. So yeah, it's it seems like it's a nice the generics and type system is pretty flexible and nothing crazy, just what you need, I think. So it might be a good balance of features and things. Yeah, yeah. All right. So that'll be it for tonight. Hopefully, I'll do another live stream a little bit earlier next week. We'll see. I don't think I'll be streaming during the weekend unless I don't know. I'll feel like it, but I doubt. I doubt so. So, yep. Thank you for watching, and it was a pleasure to share what I'm learning. And see you next time. Tara says you survived. I couldn't. Uh, yeah. I can imagine this is not a fun thing to watch on Friday. All right. Take care, Taras. And thank you for watching, everyone.